connected to the related formulations. So first one is entering into the internal energy is a property of a system. So in that case, if you just observe the if you just observe the PV plane there, so how the PV plane? So this is the PV plane, that is this one, state 1, state 2, pressure versus volume, energy is the property of a system. State 1 changes its state 1, it is going to follow the path A, that is, this is the state 2. System changes its state 1 to the state 2 following the path A. And the system will come back from state 2 to the state 1 by following the path B. So this is nothing but this is going to execute a cycle. So this is nothing but this is going to execute a cycle. So what is meant by cycle? When you apply the first law of a thermodynamics to this particular cases, so when you apply the first law of a thermodynamics, that is Q is equal to delta U, because this EA, this delta EA is nothing but the energy of the system. That energy, either it may be the, that is it is a sum of microscopic energy and macroscopic energy. But according to the first law of thermodynamics, where I could be able to consider it as a internal energy, that is the delta UA plus WA, right? So that is this is the internal energy. This is the internal energy plus WA, where work done in this particular part. Next, there is another that is the QB. So in the QB, that is here, this line. QB, that is nothing but equal to delta UB plus WB. So this is the equation 1, and this is the equation 2. This is the equation 1, and this is the equation 2. So in this connection, if you are trying to write, because this it has executed the cycle. Once according to the first law of thermodynamics, so once the cycle is executed, then sigma W of the cycle, is equal to sigma Q of the cycle, right? So what is the sigma W of the cycle? So that is work done through the path A, work done through the path B is equal to heat transfer through the path, because this heat and work depends on to the path of the system. So that you should not forget, right? So in this way you can write. So now you can write this one as a QA minus WA, that is equal to WB minus QB. So this QA, that is here, QA minus WA, that is nothing but equal to delta UA is nothing but equal to minus delta UB. So in the same way, when a system changes from state A to the state 2 by following the path A, and it will come back from state 2 to the state 1 by following the path C. So again, you are going to prove that delta, that is the delta UA is nothing but equal to minus delta UC, right? So combining these two, then finally what you are going to get is delta UB is nothing but equal to delta UC. This is how the thing. So finally, it is going to indicate that the internal energy depends only on to the initial and final states of the system. Internal energy depends only on to the initial and final states of a system. That's why it is a point function. So that is, it is an exact differential. So here you are going to write du, or it may be the delta u, that is nothing but equal to u2 minus u1. So in the same way, that is the delta dH is equal to, that is the delta H is equal to H2 minus H1. It depends only on the initial and final states of a system. Next, ds is equal to, that is the delta S is equal to change in entropy. So that is nothing but equal to S2 minus S1. So here change in volume, that is equal to V2 minus V1, right? So it depends only on to the initial and final state. Whereas the heat and work, that means you have to write it as a d bar W, or you have to write it as a d bar Q, right? So in that situations where you have to represent the when work is following the path A, so that is the W1 to 2, right? So in this way, or either you can write it as a W1 to 2, or here, so this Q1 to 2, or you have to write this Q1 to 2. So this is how. If you are writing it as a Q1 minus Q2, it is absolutely wrong. If you are writing the work as a W1 minus W2, it is absolutely wrong. So this the students has to understand this particular thing connected to this particular side. Okay. Hope they improve that internal energy is a property of a system. Hope the students have understood this particular difference between the heat work transfer, that is exact differential and inexact differential. Prove that internal energy is a property of a system. So all these particular things it is covered in this particular slide. Prove that internal energy is a property of a system, that is it depends only on to the initial and final states of a system, right? Next one is so this is how the things are there. So finally, where you could say that the cyclic integral of any property is zero, because the final state is identical with the initial state. So the cyclic integral of dE is equal to 0, or the cyclic integral of dV is equal to 0, right? So the cyclic integral of any property is 0. So this every student has to observe this one. So the energy E is nothing but this capital E. It is an extensive property. But when you write this specific energy, E is equal to E, that is joule per kg. So this is going to become an intensive property. So the student has to understand the difference between extensive property and intensive property. Next one is prove that energy of an isolated system remains constant. Prove that energy of an isolated system remains constant. So that here, if you take one system, so it is an arbitrary system, and it is insulated. That is here, no interaction. That is the system isolated. Here I am calling it as a isolated. So this isolated system is isolated. Now, when the system is isolated, so in that case, heat transfer is 0, and already the work transfer is also equal to 0. So when you apply the first law of a thermodynamics, that is Q is equal to, already it is arrived. So it is a delta E plus W, or you can write it as a internal energy delta U plus W. So this Q is equal to, right? So here this energy means when I talk about the energy, always I will observe that it is a macroscopic energy and microscopic energy. But when you apply it specifically to the first law of thermodynamics, you need to focus on microscopic energy to this particular aspect point of view. So here this is 0, and this is also equal to 0. So that means delta U is equal to 0. That means this du is equal to 0. So that means U is equal to constant. So this is how you have to derive the expression. So that is so the energy of an isolated system always remains constant. Always remains constant. So this is how you have to prove the expression for this particular point. The second one is the third one is perpetual motion machine of first kind. Perpetual motion machine of first kind. So you observe the diagram here. Observe the diagram. So any engine. So this is the engine. So engine is going to produce the work when you will supply. Say suppose if you are giving the 5 watts of energy, then in this case if you are going to be getting as a 1 watt, then it is okay. But according to this perpetual motion machine, it is a fictitious definition, or it is a fictitious machine. what this is going to define, or what this is going to state, that there is a machine which continuously produces the work output without taking any heat input. There is a machine which continuously produces the work output without taking. That means here the Q is 0. So that fictitious machine is not possible. So here first law states that it is a general principle of conservation of energy. Energy is neither created nor destroyed, but only, that is the first law, what it says, that the one form of energy can be transformed to the another form. So that you should have to observe. So there can be no machine which would continuously supply mechanical work, that is here. Continuous supply mechanical work without some other form of energy disappearing simultaneously in this one. So the converse, here the converse of PMM1 means, when you are continuously giving some work input to this one, here the heat has to reject. But if heat is disappearing, that particular machine is also